he's been traveling the world, bringing this talk to some of our most innovative, users and customers worldwide. I've been on a few of these world tours with him, and I don't know if you remember this, Rick, but the first time we met in person was in Dallas at this huge event. We introduced ourselves. Rick had just joined from AWS, myself from Google Cloud, and you attempted to make a joke about Google Cloud Data Store. It didn't land. And the reason why no one's laughing right now is because only someone like Rick would understand that. I didn't get it at all. I didn't get it at all. But I'm so proud to introduce him. I can attest that Rick is truly an evangelist when it comes to NoSQL. There's nothing like hearing a Rick Houlihan session. I'm so excited that all of y'all get to hear this. He is maniacal about document structure and flexible schema. He's obsessed with the end user. That's all of you. Like I said, he travels the world to speak with people like you, and how to help you build the next big thing on MongoDB. In today's talk, from RDBMS to NoSQL at enterprise scale, which I've heard so many times and I learn something new every time, he'll break down real-world workloads and dive deep into the core value of MongoDB for SDEs and product stakeholders. And with that, I guess it's my pleasure to introduce the inimitable Rick Houlihan.
Great, thank
Enjoy.
you. Thank you, Rhett. Thank you everybody for coming and hearing me talk today. As Rhett said, I'm the Director of Developer Relations for Strategic Accounts here at MongoDB. My name is Rick Houlihan. I have a long history in NoSQL technology. And actually, I started at MongoDB. Although this is my second tour, and a few months after Rhett, I actually spent a year on the Enterprise SA team about a decade ago. So very familiar with MongoDB and the evolution of technology. I spent many years at AWS, and that's literally what we're going to talk about today is the lessons learned from that experience working with the Black Belt team for NoSQL technologies at Amazon Retail. One of the things I like to talk to when I have the conversation with teams about why should you choose NoSQL technology, is really why did Amazon make that choice, right? Amazon was a large enterprise. The retail organization it's like any organization. I think I heard today in an executive call that I was on earlier, executives say we need to have business reasons to make these decisions, not just because we like the technology, right? And a company like Amazon doesn't make this decision just because they like the technology. So we'll talk a little bit about some of the drivers and some of the reasons why that decision was made. And then we're going to get into what does it really take to make that kind of a transition to enterprise scale, right? A new technology like NoSQL, it's disruptive when you think about what your developers already know, right? And so how do I actually drive a new technology into an enterprise organization like Amazon? So what is the reasons why we make this move? How do we make that transition? And really, how do you make it work? And that's what my team really focuses on. We'll talk a little bit about the process that I go through to kind of help developers get over the hump when we talk about relational database technology and NoSQL technology and how does it actually all work. And then we're going to get into an overview of what the plan looked like when we actually made that move and what was the execution strategy that led to the success of that project. All right, so the first thing we'll talk about is why NoSQL. When you look at Amazon as an organization, it wasn't really born in the cloud, right? Amazon Retail was born in 1995, and there was no such thing as the cloud. As a matter of fact, the first cloud service launched in 2005, EC2, was not suitable for business workloads that actually drove the business. And so, when you really think about it, it was a $5 billion company before service-oriented architecture even became a standard, right? The famous letter that Jeff sent, the missive that said all development from here on at Amazon shall be service-oriented architecture and microservices. This was a tremendous shift in the paradigm of enterprise application development. It was actually foreshadowed a move that the industry made over the next several decades. Till today, we look at SOA as it's really a foundation of all modern application development today, right? And again, by the time 2018 rolled around, when we look at Amazon's core business, it was not built on SOA. The core business was actually built on monolithic services, right? The herd orchestration engine, right, was a monolithic stack. We had the largest Oracle RAC deployments in the world. We had 3,000 Oracle Server instances. We had 10,000 workloads deployed, a little over 10,000 workloads deployed, and 25,000 developers globally. And this is in 2018. Today, it's probably twice that many or 3 times that many developers in the company. So when you look at what was the real mission when we went into this project we called Rolling Stone. The real mission was to reduce the cost of the relational database infrastructure, right? That was the big line item. The Oracle license was huge. We didn't want to write that check anymore. And if you think about what was going on in the enterprise, it really had nothing to do with replacing the relational database at first, right? The original mission was, let's get rid of this Oracle license. It's killing us. And the original idea was we're just going to bundle all those little relational workloads up into their own RDS instances, and we're going to drop those things into AWS, right? So that was the original idea. Didn't really work out that way when the team started looking into the problems we had to solve, right? That's not, there was a process that the teams had to go through to understand what technology to actually, or how to make that migration. And what was interesting was that it's a process we've been through many times, okay? When you think about the history of data processing, the relational database wasn't always here from the dawn of time, right? It wasn't the first thing we ever had. As a matter of fact, the first database we ever had was the one we were born with, right? It's between our ears. It's highly available. When my eyes are open, it's online, right? It's a single user system. Questionable durability, zero fault tolerance, right? We're not going to build enterprise services on this. So we had to actually do something else. What did we do? We started writing things down, okay? So storing structured data, that's the definition of a database. What is a database? It's a system to store structured data. We started writing things down in ledger accounting, drove public and private sector services for millennia, many millennia, until the 1880 US Census, right? And along comes Herman Hollerith, and he's tasked with processing all of that data, and it took him 8 years of a 10-year cycle, and he invented the machine-readable punch card, and the punch card sorting machine, and the era of modern data processing was born, right? So rapidly we started pushing the edges of this technology. Started to become too expensive to use, too slow to use, and that's really what it comes down to in database technology. It's about data pressure. Right? Data pressure is the ability of the system to process the amount of data that we're asking it to process at a reasonable cost or at a reasonable time. When one of those dimensions is broken, it's a technology trigger. We've had many of these over the years, right? This is just a few of them. Paper tape, magnetic tape, distributed block storage, random access file systems, and hierarchical management systems. These were the first real databases, right? Hierarchical management systems, IBM's IMS. Right? This was really what was threatened by the relational database in the late 70s, okay? And actually, when we look at the relational database, when it was delivered, the man who actually invented the relational database didn't believe that he would ever be able to do it because his mission, Edgar Codd, his mission was really to provide a system that allowed people to ask questions of their data without having to write code. That's what he wanted to do. It's in the abstract of his paper, right? The relational data model for large shared, storage systems, whatever. I can't remember the exact title. The reality is that he doubted he could do it. Why? Because the time complexity of joining data from a relational in a normalized database was too high, and the CPU cost of doing that, everyone theorized would be too high. Okay, now when we fast forward 30 or 40 years, we're actually asking the same question. This is what Amazon was actually faced with when they broke things down. The time complexity of the relational database was hidden by a little thing called Moore's Law, okay? But Moore's Law is no longer enabling the relational database. So if you want to ask yourself, why do I want to look at NoSQL today? This is why. And this was the question that Amazon started running into when we started breaking things down. The reality is that CPU performance was flattening in 2014, and it's been flattening out ever since. And the reason why is because the industry does not want to invest in 5 nanometer fabrication for server processing. Right? You see it in the mobile device space, mobile phones, right? These things have 5 nanometer CPU. Why? Because it's a subscription service, and that CPU in this device is a loss leader. You don't see that in the data center. Okay, so this was the equation we started looking at. Wow, the relational database is becoming more and more expensive. Why? Because of the same reasons that the man who invented it thought. If you look at this chart on the left, on this screen, right, this is the top 500 supercomputing clusters in the world, right? That's called the top 500. Now, they have been unable to meet Moore's Law performance increases consistently year to year for almost a decade. So this is not something that I'm just making up. This is the data that's bearing it out. These guys invest in everything they can to get every petaflop they can, and not even, they can't do it. You're not going to do it in the server processing space. That's the reality, right? Per core performance, power consumption per core, it's all going flat as we start to see the unwillingness to invest. And that's because Moore's Law is not a law. Okay, Moore's Law is a financial equation. How much is the industry willing to pay to double the transistor density in the CPU every 2 years? Right now, not enough. And that's the bottom line, and I don't think it's going to change. However, the cost of storage continues to fall, right? Today we pay pennies for terabytes of data, really, literally. It's crazy how cheap storage is getting. So the words of the man himself, Edgar Codd, right? These are excerpts from his paper on normalization, the advantage for storage, the advantage for bulk communication between systems because of the deduplication of data in the normalized format. That's fantastic. However, denormalized data is going to increase the efficiency of the CPU. And this is really where my team focuses. This is exactly where Werner and his team started focusing when we started breaking things down. We'll get into the actual access patterns in a second. But the reality is that normalization costs, and even in the lower left-hand corner there, you can talk about a common mistake I see in a lot of relational databases today is over-normalization, right? These little lookup tables, which is 10 rows, and then you're joining that in on every query, right? Like event states, info, warning, critical. You know, it's immutable data. And even Edgar Codd himself said, if it's immutable data, then go ahead and denormalize it because there's no cost in denormalizing it. Right? The cost of the CPU in joining it is much more expensive, right? So he's even in his fundamental paper, right? The foundational paper that was the basis of every relational database today, the founder of the relational database was telling us that denormalized data is going to increase the efficiency of the CPU. And this is really, really important when we get into looking at what kind of applications we build today. Because one of the things that we start to talk about is like why NoSQL, when NoSQL, right? There's always been this kind of column between the two technologies. SQL is kind of the language of the relational database and the language of data that everybody understands for the last 40 or 50 years. NoSQL, lots of new systems, new technologies. You know, we saw a description earlier today of the Mongo query language and whatnot. And if you break things down, what it really has been in the, up till recently, there's been this kind of line between the OLAP and the OLTP workloads, right? OLAP workloads, they're ad hoc queries. We don't know what questions are going to be asked, right? The analyst comes in today, tomorrow, he has a different question, he writes different queries. He's going to use the language of data that he understands, SQL, to do that. The interesting thing about OLAP workloads is they're not high velocity, right? You don't run thousands of OLAP queries a second, right? They're not latency sensitive. Typically, they run a couple times a day, maybe once a week, once a month, end of quarter reports. We don't care if they come back in 100 milliseconds or a second or two. They don't need to be totally efficient. The other side, though, OLTP workloads, 90% of the workloads that we write code for are OLTP, right? Automating a business process. Those queries are well understood. It runs that same query 1,000,000 times a day, right? Hundreds of times, thousands of times a second. It's not going to change the query every single time, right? It needs to run that process. It's going to run the exact same query every time. So now I can start to actually modify the data model, tweak the data, and we're going to see this in a second when we get into the actual modeling here. And Daniel showed you some techniques earlier, but the reality is if I optimize the data model for the access pattern, for my high frequency patterns, I can save a lot of money. And that's really what we started finding when we started looking at things at Amazon, right? I love this quote from Mark Twain, right? I think he's a time traveler. He was actually an early investor in data storage technology, right? He invested, I think, the Linotype or something like that. But data is like garbage. You better know what you're going to do with it before you collect it. Yes, I totally agree. I've seen a lot of that. Access patterns drive cost, right? This is what Werner found, and this is what changed the whole mission of Rolling Stone. Again, Rolling Stone was the internal project name for the deprecation of those 3,000 Oracle Server instances, and that was the mission of that project. It became replace everything we can with NoSQL because of this, right? In 2017, Werner found that 70% of our access patterns were for a single row of data on a single table, and that 20% more were for a range of rows on a single table. If you think about it, that makes perfect sense. Why? Because it's all OLTP workloads, right? 90% of the things we write code for are OLTP workloads. OLTP workloads are extremely write-heavy. So when writes are always going to hit a single table. They're going to hit a range of rows on a single table, right? They're not going to go, you don't write data and have it go and write across multiple tables, sure, inside of a transaction, but that's also another overblown construct you hear all the time, ACID, ACID, ACID. Nobody uses ACID, right? We don't lock tables. We don't want to lock the rows of a table. We don't want to see deadlocks, right? Typically, you're going to code the application to use optimistic locking. You're going to use two-phase commits. You can't have ACID transactions across systems of record anyways, right? So, bottom line is, again, what it came down to is 90% of the access patterns hit one table at Amazon. But 50% of the infrastructure was dedicated to supporting the other 10%. Why? Because the time complexity of all those queries, right? The reality is it's all about relationships. Every single application we build, we need to be able to express these relationships, and we need to be able to do it efficiently, or we can't use the technology. And this is where the application, the developers at Amazon were breaking down, okay? Was actually using the data efficiently to model relationships, because they all heard about this non-relational database. If it's a non-relational database, then I don't have to worry about relationships anymore, right? That's absolutely wrong, and it's kind of counterintuitive to the developer's mind, right? We all understand that the data has relationships. The conditions of my query define those relationships. If I can't express those relationships efficiently, then the system's not going to work very well for me. Okay, so if we look at and break things down, and why is the relational database its day's done? Okay, and this is why. And it's never going to get better no matter what anyone tells you. And one of my favorite quotes in software engineering is from Grace Hopper. And believe me, I founded my career on this. I built my career on this. One accurate measurement is worth 1,000 expert opinions, all right? We can sit here and talk all day. Code it, show me, measure it. You show me a relational data model joining tables, I'll show you a NoSQL data model that's going to smoke it every single time. And this is why. If you look at the relational database, right, we use this third normal form to try and map these entities together. This is a product catalog. Think of Amazon's product catalog and the use cases for a product catalog. Get me a product by ID. Get me a product by type, maybe by manufacturer or whatnot. But it's always product-centric, right? I always want to get kind of the view of the product. So if I put that data in a relational database, I store all these little bits of information about the products in different tables. You think about the joins I have to make to get a list of my products, different queries, different levels of complexity, right? Maybe I don't necessarily want to do that for the product catalog. Maybe what I want to do is kind of pre-join those rows into these documents and embed those child rows into the correct data structure, because when I select a product by ID, I don't want the CPU hopping all over the disk, reassembling that view. I just want to go grab it. Now in this particular workload, this works very well. In others, maybe not so much. But the reality is that there's always a data structure that's going to be more efficient than joining the tables, because if we actually put data on these tables and we start looking at what needs to happen here when we join the data, let's look at some of these queries, right? Select the book product, not too bad. It's a one-to-one join across two tables. But the time complexity down below, this doesn't get better when you start adding tables, right? Join through the one-to-one to the one-to-many. Uh-oh. And that's CPU cycles, folks. This is infrastructure. This is why when Werner started breaking things down, right, 50% of our infrastructure went to support 10% of our access patterns, because these reads are expensive, right? This is really what the relational database does. An optimized relational query is going to join indexes across tables. That's what it's built to do. And it's going to try and do it as fast as possible. And we're going to introduce all kinds of new technologies to try and prevent it from doing this over and over again, right? We'll have caches up in front of the database that we're going to hopefully hit the cache. If it's not in the cache, go hit the database, because we're trying to offload the CPU hit from doing this, right? But it doesn't get any better. As you get to the many-to-many, you can see it just explodes. And these are simple queries, right? These are very, very simple queries. If you're a DBA, you haven't seen stuff like this since, I don't know, you were learning how to normalize a data model, right? This is, when you get into real production SQL, you're going to see lines of SQL that are hundreds of lines long with nested SQL in the middle, and the time complexity here just gets tremendous, right? So when you start running these queries at high velocity, you just start eating infrastructure alive. Now let's take a look at what happens in NoSQL to actually model these relationships efficiently, and there are ways to do it. One of the things we learned very quick at Amazon was that applications don't use data in big, large chunks, right? Well, they do. Those 10% of those reads needed like joins and bigger views of data, but applications tend to use data, the high velocity patterns use data in bits and pieces, right? All those little inserts, right? Inserting rows on tables, updating rows on tables. Those are small chunks of data that are moving around, right? So modeling the data efficiently matters. Sometimes the big, large embedded document hurts you if I'm updating little bits and pieces within that document. So I need to show you how to express relationships and do it efficiently in NoSQL. So the way we're going to do this is we're going to build essentially those key value access blobs, right? And every one of these things that describes a product is going to have some data that describes the product. In this case, I've just got a couple attributes in the data section. There'll be many more in a production system. I'm not really interested in the metadata that describes the book. I'm interested in the data structure that describes the relationships. And if you look at these target array, this is the interesting part of what we're going to get into here. But this target array, really, these are pointers to the other documents in the collection that I'm related to, right? So if you think of it, the book might be related to its author, it could be related to a publisher, right? It's going to be related to itself, obviously. And if I want to get the information for the book, I can select by underbar ID equals Frankenstein. I'm going to get that book metadata. That's going to be an O-log-N query, right? It's already less time complexity than the two-table join. If we get into the album, similarly, right now, instead of the time complexity explosion O-log-N, it's key value lookup, getting a single document. Now, this document might be giving me all the information about all the things it's related to, which we're going to get into in a second, but it's telling me what it is related to, okay? And again, the time complexity of all these key value lookups is O-log-N, because it's just an index lookup, right? Same thing with the movie, through this many-to-many, O-log-N. I can express the information about how these things are related to each other. I can get the information about the movie easily enough. But when we add more dimensions is when things start to become really interesting here. Right now I'm going to add the actors, I'm going to add the authors, I'm going to add the producers and the directors and the songs. And all these things we're going to tag with the relationships to what they're related to, right? The song will be related to the musicians that performed it, the writers that wrote it, whatnot, and so on and so forth. And when we index that target array, okay, this is when things get really interesting, because now if you think about what the relational database, what does it do? It joins indexes, okay? If I took all the rows, which I've just done, I took all those rows, I build objects that are relevant to the access patterns, right, that contain the data that I need to get at most frequently, and I put them in the same collection, and I index them on a shared attribute, I don't need to join them anymore. They're already joined. The index is shared across all objects. All objects live in one collection. If data is accessed together in a NoSQL database, it should be stored together, either in an embedded document or the same collection. Because then, now I can look at this, get me all the books where anything that targets Mary Shelley, right? The books she wrote, the people she's related to, it's O-log-N. I'm just querying the target IDs of all those relationships on all of those data structures, right? Those are the key. This is expressing how things are related to each other. And when I index those relationships, one of the best aspects of the document data model and of MongoDB are multi-key indexes, because you get this type of functionality. Select everything where a song appears on. I can get all the albums that it appeared on, all the musicians that performed it, the studio that recorded it, all that information, so on. Get me everything that targets Tom Hanks. People can be actors, they might be producers, they could be publishers, they could be many things. I could get, all the relationships, everything that is related to a particular individual in a particular way, right? Because this is what I've done. I'm indexing target ID, target type, and that tells me what documents are related to each other. Again, this is the trick in NoSQL, right? We want to optimize your high-frequency patterns by creating documents that map very well to those small writes that we see 90% of the time. But those big reads need to join those documents together and be able to produce those views. So to be able to do that, if we store all of these documents in one collection and we share the indexes across them, essentially now I can query on those index dimensions, which are my join dimensions, and I get the similar data that I'm looking for that I get from the relational database. And again, time complexity, right? Time complexity, O-log-N, O-log-N, O-log-N. It doesn't matter what I'm querying for. It's just an index lookup. So we're talking about an order of magnitude inefficiency here. So this is really what happened. This is exactly what happened at Amazon as we went through this exercise of why do we want to replace the relational database. It really wasn't that exercise. The exercise was let's replace Oracle. And then it became, well, boy, this relational database is getting expensive. And oh my gosh, the joins are the thing that are killing us. Well, maybe the NoSQL database is a better option here, all right? Because we can drive efficiency like this, and you can't do this with the relational database. There's just no way to do this. And even though you can model your data this way in a relational database, the storage engines aren't built for it, okay? So the document storage engines you see in NoSQL databases like MongoDB are orders of magnitude more efficient than what you might get from Postgres using JSON-B, using the exact same data model, because in relational database, it's all about columns and rows, and that's how the data is stored. And if it gets into a big document structure, you're going to be needing off-row storage. Off-row storage is inefficient, right? It's all about measurements. I can tell you right now, you measure it. You go, you data model it, you model your joins, you model your single table implementations like this, single collection implementations like this. You'll see orders of magnitude efficiency, and that's just the way it is. Now, it doesn't work when you don't know how to use it, all right? And this is the key that we found at Amazon. One of the things that my team spends most of our time with is helping people get over this hump. If you look at any kind of technology in any ecosystem, the adoption curve down below pretty much describes how people learn it, how many people in your organization actually understand it. And in the beginning, not many, right? There's a technology trigger. In this case, it's data pressure. The system's too expensive. It's too slow. In the beginning, not a lot of people understand how to use it, but a few people had some success, so everyone tries to use it. And we saw this. This was the biggest lesson learned from Amazon, that peak of inflated expectation where everybody said, okay, we're all going to go run and use NoSQL, but it doesn't work so well. And the reason why can be explained in one service, one team I worked with, the shopping cart team. Everyone knows the Amazon shopping cart, right? When you add items to the shopping cart, you don't add items all at once, you add items one at a time. A lot of people add items to their shopping cart. They'll leave them in there for a week or two. They'll come back in. They'll check out. They'll say, I don't want this. I don't want that. I don't want this, right? So you're kind of working with the data in bits and pieces, right? Individual order items. Now, at Amazon, of course, we use DynamoDB. DynamoDB is absolutely merciless when it comes to cost. If you're writing and reading data that you don't need, you'll really notice it fast, right? So if you think about how people use the data, right, they kind of add an item to the cart. It's about a kilobyte of data that gets added to the shopping cart, and the team had built a DynamoDB item, and they're putting an array of order items inside there, essentially building a document for each shopping cart. Now, so you come in, you add one item, it's one WCU, you add two items, guess what? I get to read the other item, and I get to write it back, that's 2 WCUs. I add a third item as 3 WCUs, I delete the third item as 3 WCUs, you get the idea, right? The more items I added to this cart, the more expensive each operation became. So the team came back and said, we can't use DynamoDB, right? It's too expensive and it's too slow. And NoSQL doesn't work. And it kind of sent shockwaves through the whole operation, right? Everything we talked about didn't work. What the heck is this? Well, the reality is when we changed the model a little bit and we said, okay, well, let's just create indexed collections of items and say, an order item goes in there, it has a shopping cart ID, we'll call that the partition key. The sort key will be the ASIN or the SKU of the product. And now I'm essentially adding items to a partition on an index where I'm saying, okay, let's put item 1, item 2, item 3. Every single operation is 1 kilobyte. I need to update the item, and that's the other thing is the order items had their own life cycle, right? So they would be updated from this fulfillment center, shipped on this date, whatnot. As you can see, it kind of triages the order once you place it, right? So a lot of updates coming into those individual items. This architecture facilitated that. The former one didn't, right? The former one was a disaster, as a matter of fact. It almost tripled the cost by estimate. This is one of the best things about Amazon that kind of taught us these lessons. At Amazon, you measure everything, right? The results, you got to prove it, right? You got to go in, you write the narrative, you write the document, everyone reviews it, we approve it. Now in the end, when you do it, you better vet it, you better verify it, and the measurements weren't coming back right, and this is when we start figuring stuff like this out. And that's when once people start learning how the technology works, you have a better experience, right? And this is really that slope of enlightenment comes in when that early majority arrives, all right? So in most organizations today, where are we with NoSQL? Well, we got a lot of people who think they know how to use it, but don't really use it very well. We're in that early adopter phase, probably. We're kind of crossed the technology chasm now. We got clear market leaders like MongoDB, out there that are establishing themselves as the choice to make. So, but we're not quite in that early majority phase because most developers today, they have a tough time modeling with NoSQL databases. This is what my team does, right? My team focuses on building tailored engagements for our strategic customers. We learned at Amazon that one of the most effective ways to learn how to use the technology is to learn how to solve a problem that you're working on with that technology, right? Developers are really, really good at understanding SDKs and tearing apart APIs and going through documentation that's available online. So workshops, hackathons, and all that, those are great. Those will teach them something. But most of the time when developers were leaving those sessions when I was at Amazon Retail, they didn't really know how to solve their problem, so they didn't really get much from it. So what we did was we started saying, okay, look, when I go to customer sites, we do the brown bags and the technology overviews, but instead of the workshops and the hackathons, we actually turn the workloads into the workshop. Our customers register with us for design reviews. We actually have open sessions now. MongoDB Day is open to the public for this as well. A big Move to Mongo event yesterday. And essentially what we're trying to do is give you an hour of time with the data modeling expert to show you the way, give you some breadcrumbs, give you a trail to follow. Developers are incredibly innovative. Most of what I learned about NoSQL, I learned from the people I work with. because they know their data better than I do. They know their access patterns better than I do, and I can show them a path, but they're the ones who are going to go off and iterate on it. I just learned a new pattern the other day. It's a variation on the attribute design pattern that we have. It's called the attribute group pattern, we're going to call it, right? I learned it from a customer who took away the guidance we gave him and came back with an improvement on the design pattern I'd never seen. And this is what happens when you show developers how to solve their own problems with the technology. They learn, they teach you. And so that's really what my engagements are about. They're an exploration of NoSQL data modeling. It works both ways. I learn from my customers, they learn from us. And it's about whiteboard sessions with subject matter experts so you can get kickstarted in your project. And again, these are available. We're running these things as much as we can, available to the broad public. My team focuses on strategic accounts. If you work for one of our strategic accounts, then talk to your account team. We can set up these engagements as well. And if there's anything you can take out of my session today, I would say NoSQL does not mean non-relational. As you noticed, I don't use that term unless I'm telling you it doesn't exist. Right? The reality is non-relational data is what's on the hard drive before you format it. Right? Nothing you care about. It's static in the air between the radio channels. Right? If it's data that you care about, it's relational, and you need to be able to express those relationships in order to be efficient with technology. ERD still matters. Right? The relational database, its day is come and gone. You know, distributed SQL, I can make it scale. I learned in physics in high school that with enough velocity, anything will fly. Okay? So the bottom line is the relational database can solve any problem. Can it do it cost efficiently? Hell no. And this is why Amazon moved away from it. NoSQL is really a great fit for most OLTP workloads right out of the box. And the SQL API that we all have today makes it just as suitable for OLAP workloads. Right? There's no longer that big line in the middle that says relational this side. It's not NoSQL anymore. It's no RDBMS, and really for good reasons. All right, so that's what I got for you today. Thanks so much for hearing me talk, and hopefully this was a good session for you.